Okay, I'm going to go ahead and get started. So this morning we covered the ab initio series in a whirlwind, okay? And we also touched on the topic of single reference and multi-reference calculations, okay? So all of that goes to the form of the Hamiltonian. And I went over the fact that if you want to include this all-important electron dynamic correlation, so the electron-electron interaction that's dynamic, you have to go to a post-SCF calculation. So Hartree-Fock does not include that type of electron correlation. So you have to go to MP2 or higher, and that has substantial increase in computational cost. Okay. So one of the other things I mentioned was that there was something called density functional theory, which also includes this dynamic electron correlation, but for about the same cost as Hartree-Fock theory. Okay, and that's what we're going to talk about this afternoon, is what is this thing called density functional theory? Okay, so first let's talk about what a functional is. So a functional in mathematical terms is just a function whose argument is also a function. So it's called a functional. Okay, so since we have the density, and the density is a function of the coordinates, density functional theory, it's a function of a function. Okay. This has been around for a long time. It was developed in 1964, the Hohenberg-Kohn theorem, okay? But it really hasn't been implemented heavily until somewhat recently. Okay? In the last 15 years is where it's really taken off, okay? 15, 20 years. All right, so the basic premise is that there's more information in the wave function than we truly need. Okay. We really only need a good description of the density, and we can get the energy and the properties from just the density. And that's the premise of density functional theory. So if we can get a good description of the density, then we have everything that we need. So in theory, density functional theory would be ab initio, variational, and size extensive, okay, which would be wonderful. It's all the properties that we want, includes dynamic electron correlation, would never go below the energy of the true system, and you could use it for reaction chemistry. The problem is we don't know the true form of the functional, okay? We don't have the exact functional form. What we have are approximations, okay? So there's a number, many functionals that are out there. Okay? So current implementation of DFT is not strictly ab initio, it's not variational, and but it does retain the property of size extensivity, okay? So the energy equation is very similar to what we saw for the Hamiltonian of the many electron problem that was applied for Hartree-Fock and then perturbation and the other ab initio series. Okay, but here we're applying everything to the densities. So we have a kinetic energy operator, it's a function of the density. We have the nuclear electron term, which is a function of the density. Electron-electron term is a function of the density. Okay, the kinetic energy correction term. Okay, so this is new. We have a correction to the kinetic energy due to the interacting nature of all electrons. So this kinetic energy term doesn't have the interaction term in it, so we have to have a correction for it. And then we also have a correction for the electron-electron repulsion term. This is the non-classical part. This goes to the exchange part for the electron-electron repulsion term, okay, which is also a function of the density, or the electron-electron interaction term, sorry. Okay, so if we write this equation out and expand some of those terms, these are the ones that we're more familiar with, okay, where you have the kinetic energy operator, the nuclear electron term, and the classical electron-electron term. And then this is the exchange correlation term. So when you go to look at functionals that are available in the DFT realm, they talk about them as exchange correlation terms, and that's where this comes in. The exchange correlation terms. And the exchange correlation terms are those corrections to the interacting nature of the electrons, the kinetic energy term, and the electron-electron interaction term that's non-classical, okay? So DFT exchange correlation falls into this. So this is just to illustrate that density functional theory is solved in an iterative fashion, just like Hartree-Fock theory. Okay, but instead of using the Fock operator, we're using the Cohen-Sham operator. So we have the one electron operator, okay, and then we have the additional exchange correlation potential that's in here. Whereas Hartree-Fock only has, here's my one electron and I'm interacting with the smeared out cloud. With density functional theory, we have the potential term that includes some of that dynamic electron correlation, okay, with this term. But it's still a set of nonlinear equations, so it still needs to be solved iteratively. And there's one extra caveat there. This can't be solved purely analytically, so it has to have a numerical component. We'll talk about that in just a minute. So that's one of the other major differences from Hartree-Fock theory, okay? So this exchange correlation term, like I mentioned, can't be solved analytically, so it has a numerical component. And what it has is a grid of data points. And this grid of data points is centered around the atoms. Okay. I'm sorry, I should have updated this with Gaussian 16, but I'll talk about that in just a minute. So it has a grid of data points that are spherical around the atom. And the number of points on each sphere is not necessarily the same. So you do have a larger number of points on each sphere around the atom, but for bigger atoms, they'll use what's called a pruned grid, where it decreases the number of points on each sphere close to the atom because the sphere is smaller. Okay. But the consequence of this is that we have a numerical component for DFT, all right, and the quality of that grid affects the results. Okay, so in Gaussian 09, the default grid was 75 shells with 302 points on each shell. Okay, and if you have a pruned grid available, it decreases the number of points on the shells near the nucleus. Okay, so if you have a very large floppy molecule, so something that has soft modes where the ligands can move easily with a small amount of energy, okay, and we had Gaussian 09, the default grid was ultrafine. The default grid was fine, okay? They suggested that if you had a big floppy molecule that you use an ultrafine grid. In Gaussian 16, the default grid became the ultrafine grid. And when the next release comes out, I suspect that the grid will get even tighter, okay? So that means you have more data points, it's more computationally intensive, okay? And this comes because the computers are getting faster, the molecules are getting bigger, we're applying them to larger systems that have softer modes, and so they changed the default of the grid. So the reason that I'm bringing this up is if you're going to be comparing the energies, say you're going to calculate the delta G of reaction, you have to use the same grid across the board. If you change the grid on one of the molecules, you have to go back and recalculate all of the other ones to use the same grid. Okay, like changing your level of theory, you can't do that. Changing the basis set, you can't do that. The grid has to be consistent also. Okay. So going beyond that, even if you're just using a single program for that, if you go from one package to another, the default grid is probably going to be different. The implementation of the grid is going to be different. Okay. So if you perform a Hartree-Fock calculation in one piece of software, with a basis set that you know what the coefficients and exponents are, you should get to within the precision of the machine the same exact answer if you perform Hartree-Fock in another piece of software. Okay, because it's analytically performed, you should get the same answer. That is not true with DFT. You're not going to get exactly the same answer because there's always variations in the grid and the way that it handles the numerical component of DFT. There's also some other subtle modifications that are often slightly different in the implementation of the functionals, okay? So the reason that I'm pressing this point is you want to stick with the same piece of software when you're doing your research. If you need to move to a different piece of software, you had better calibrate and make sure that you're getting the same results as the previous software that was used. Or if you change major releases from, say, Gaussian 09 to Gaussian 16 in the middle of a project, you're probably going to run into problems. Okay, so you generally want to stay with the same major release, okay, because of the numerical component of density functional theory. Okay. So there's a number of different implementations of density functional theory. There's the local density approximation, the gradient corrected or generalized gradient approximation, otherwise known as GGA. There's something called meta-generalized gradient approximation, hybrid methods, long range and dispersion corrected functionals, double hybrid DFT, and what we'd really love to see is including the unoccupied, which would be multi-reference DFT. So we're going to cover what all of these mean for its implementation. So when density functional theory was first applied to calculations, it was generally in the solid state kind of metals realm. It was heavily used in physics, but not so much in chemistry. And that was because the first implementation was local density approximation. And this was the energy was derived with the function of just the density, okay? So the Slater exchange term was just the density raised to the 4/3 with a coefficient of 2/3, okay? There was another one that was LSDA, which looked like this. So it was just the density raised to the 4/3 with a coefficient of 0.75. And then there are these correlation terms, which I think I have on the next slide, do I? Yes, okay. So the correlation terms look like this, but the thing that I want to point out here, I'm not going to go through these equations, is that everything is just a function of the density, okay? So here it's just the density, and then there's a couple of parameters. There's this A, this X0, B, and C. These are the fitting constants, okay? And I believe that these fitting constants were for the density of an electron non-interacting cloud. I can't remember for what element, but that's how they did the fitting. So there's a few parameters in there that they fit to experimental data, okay? And both the exchange and the correlation terms are only a function of the density. The problem with the energy expression only being a function of the density is it doesn't allow for rapid changes in the density in space. So this is why DFT was historically used when it was first implemented in metals, because the density is not changing rapidly in space. So it got reasonably good results for solid state metallic systems, but it did really horrible for molecular systems, because in molecular systems, the density is changing rapidly in space. So that's where the gradient corrected or GGA methods came in. When the GGA methods were developed, it started to be used more heavily in the field of chemistry, reactions and molecules, okay, and looking at the properties of molecular systems or non-metallic solid state systems. The major difference is that the energy expressions are not just an expression of the density, but also the gradient of the density, which allowed for that description of the rapid change in the density in space. So exchange term, the most common one that is still used today is the Becca exchange term. You see in the literature, it's pervasive, it's still all over the place. So this is just a correction to LDA. So they took LDA and they added on a correction which includes the gradient of the density. Another one that you might see in the literature still is PW91, Purdue-Wang, developed I believe in 1991. And again, it's based on LDA, but they added in a gradient of the density, okay, to improve the results for molecular systems. Correlation terms for GGA, DFT, LYP, still heavily seen in the literature. Looks like this, again, including the gradient of the density and a few parameters in there. And this was developed by fitting data for the helium atom. Okay, so they developed LYP fitting density or fitting the data to the helium atom, and then you can apply it to whatever else. Another one that you'll still see quite a bit is P86, developed by Purdue in 1986, and PW91 for these correlation terms. Okay, so it's very common to have an exchange component and then also a correlation component. Now, theoretically, you can mix and match them, but some go better together than others. Okay, so this is just a listing of some of the common ones, for straight GGA, the BECA, the PW91 for exchange, and then a bunch of different correlation ones, and you put them together. So BLIP, BP86, PW91, PW91. Okay, and there's a lot of them out there, a lot of functionals. We will have a summary slide that lists functionals. So these were some of the originals that were heavily used and that you still see in the literature today. They're well-balanced, well-behaved functionals for the most part. They may not get you the most accurate number, but they're well-behaved and give you reasonable numbers often. Okay, so after that was the development of the meta-generalized gradient approximation, or tau GGA. And this includes not only the gradient of the density, but also the Laplacian of the density, the second derivative of the density. Okay. So a common exchange term for this is TPSS. Common correlation is TPSS. So you put them together, it's TPSS, TPSS. Here's the fun part. The keyword is TPSS, TPSS, but when they reported it in the literature, they just say TPSS. Okay, so often there's a difference between the functional that's reported in the literature and the actual keyword in the way that you call it in the program that you're using. Okay, so don't be surprised if you run into that. There's also standalone exchange correlation functionals. Trular and coworkers have a long laundry list of functionals that they've developed for certain tasks to get, or for certain properties to get more accurate energetics. Okay, and there's a lot of them are standalone, so you don't mix and match them. You just have the one, and it incorporates both the exchange and the correlation in that one functional. So M06L is one of those, but there's a long list of them. Okay, so those were all pure DFT. So LDA, GGA, and tau GGA. Those are pure DFT that include the exchange and correlation just from the density, the gradient of the density, or the second derivative of the density, and the exchange only comes from the DFT component. One of the things that was found was that often some energetics were not as good as they were hoping for, and they realized that it was because most of the functionals are missing some of the exchange energy. So the next implementation was, or not the next, another implementation of density functional theory was to include exact Hartree-Fock exchange. Okay, so the DFT has a correction for the exchange term, but to better describe, they found that inclusion of a certain percentage of Hartree-Fock exchange was a better representation of a lot of molecular systems and their properties. Okay, and this is what you really see in the literature, are the hybrid functionals more often than not. So the most common exchange term still to this day is B3, Becca's third parameterization. Okay, it's a GGA functional, but it includes a certain percentage of Hartree-Fock exchange. Okay, and standalone exchange and correlation, M06, BMK, TPSSH, all of these incorporate a certain amount of either their GGA or tau GGA, and they include a certain amount of exact Hartree-Fock exchange. Okay, so now this is where I mentioned in the morning lecture that we would come back to talking about Hartree-Fock, and the consequence of the fact that Hartree-Fock includes the Fermi hole correlation, which is the correlation of the spin-up interaction, but not the dynamic electron correlation, which is the spin-up, spin-down. Okay, so Hartree-Fock implementations always favor the higher spin state. Okay, and this becomes important to keep in mind if you're looking at the energetics of different spin states for the same molecule. So if you don't know, because you don't have good experimental data, or you are unable to get good experimental data to elucidate the spin state of some compound that you're interested in, and you want to resolve it computationally, and you use a hybrid DFT functional, and you find that the high spin state is, say, 2 kcals per mole lower in energy than the low spin state. You have no idea which one's lower in energy, okay? Because the Hartree-Fock exchange is probably going to be over-stabilizing the high spin state. Okay, so you will have to do a series of calculations to confirm that the higher spin state is truly lower in energy than the lower spin state. Okay, you won't be able to rely on a single number, and you probably want to do both hybrid and non-hybrid DFT and compare those results. Okay. So anytime you have something that's within 3 to 5 kcals in DFT, you need to probably do some additional calculations. Okay, without that, your conclusions may not be as strong as you would hope for. Okay. Okay, so I want to make a comment about B3LYP. B3LYP is still heavily used in the literature. You will still see it in all sorts of publications. And it's not because it's the functional that's going to get you the best result. Okay? The reason that B3LYP is still heavily used in the literature is it's well-balanced, well-behaved, and often gives you okay results, okay, across a wide variety of systems. And that's why you still see it so heavily in the literature. Every level of theory can have catastrophic failures. Absolutely. B3LYP will have catastrophic failures in representation of systems, whatever property you're looking for. Every level of theory will. CCSD, parentheses, T, anything you can choose will have some catastrophic failures. Okay. The other thing that I want to point out about B3LYP is the implementation of B3LYP between different programs can be slightly different. Okay, and that's what's laid out here. So B3LYP is a combination of these different parts. So we have, you know, the Slater part, that's the LDA part. We have the Hartree-Fock inclusion. There's the Beca part. The correlation is VWN with a correction on it. And then they point out that they used VWN functional 3 and not VWN functional 5. Okay, so there's different implementations of VWN. So not only do you have the possibility of having a difference in the grid, okay, when you're doing a DFT calculation from one program to another, you also have the possibility that the B3LYP implementation might be slightly different from one program to another. And that's why it's important to be consistent with the program that you're using, and when you're publishing, to specify which program you used and the version, okay? Because there are slight differences. Those slight differences will make slight differences in the overall result, okay? They shouldn't be large differences, but they can be, you know, half kcal, depending on what you're looking at. Okay, one of the things that all of these implementations, the local density approximation, the GGA, the tau GGA, the hybrid GGA methods, the inclusion of the Hartree-Fock exchange, they suffer from a lack of proper representation for long-range interactions and dispersion interactions. So the dispersion interactions are those van der Waals interactions. So if you have the weak interaction of, like, if you have phenyl-phenyl interactions, or, you know, the famous one is the buckyballs, they're sticky. Okay? So if you have a bunch of alkanes, as the chains get longer and longer, what happens? It goes from being a liquid at room temperature to a solid, okay? And that's dispersion. That's the van der Waals interaction. It's the quantum effect, right? DFT does a pretty poor job of that with the early implementations. So what they have developed are corrections to the functionals to try to fix the poor dispersion and long-range correction for the early functionals, okay? Okay, so there's a lot of different long-range corrected functionals. Some of them also include corrections for dispersion, okay? So you can put LC in front of a bunch of stuff. The omega B97, omega B97X, which includes HAR2-FOC exchange over this one. Omega B97XD includes HAR2-FOC exchange and an empirical correction to dispersion. Yeah, CAM-B3-LYP was developed for excitations. And like I said, you can add LC in front of a whole bunch of different pure functionals. It was designed for pure functionals. So it's when you're, what functional you should use, generally you want to look in the literature, okay? Just like with a basis set, just like with whatever level of theory. But you should have a basic understanding of what that functional was designed for, okay? Especially if it's one of the more specialized functionals where you're adding on some corrections, okay? You should know what it's designed for. Okay, there's also some dispersion corrections that you can tack on to most functionals. So you can run it and you just add on this empirical dispersion add-on, and it is literally an empirical correction to the functional to get that stickiness for the van der Waals interaction. Okay, so I've already talked about this. CAM-B3-LYP has a splitting function that lets you get long-range corrections, okay, and gets better UV vis spectra calculations or excitations. So if you're interested in doing something like that, you might want to look a little bit more into the CAM-B3-LYP. Okay, so this is the paper that goes with it, and it just shows how it has that splitting function so it can get the right character. So this is an illustration if you're interested in learning more about the dispersion correction, okay, and getting this well correct. That is often poorly done with most of the functionals, okay? And here's a reference for that one. So this is just illustrating how bad it can be. So if you take TPSS or BLYP and you plot the distance, you just take single point energies of these two buckyballs and get the energy, it's completely repulsive. Okay, and B3-LYP is the same way. So really, really bad for this weak dispersion interaction. Doesn't do well with it. But if you add on the dispersion correction, then you get good results with the experimental. Okay. But if you just use the pure functional or one of the functionals that's poor with dispersion and you have a lot of congestion, you have a lot of van der Waals interactions, your results are not going to be as good as they should be, if not completely wrong. Okay, you can look at this at your leisure. It's just showing how the correction can really improve your results for all of these pi-pi van der Waals interactions. Okay, so this is the summary page that lists the functionals that are available in Gaussian 16. And they may have added more in the latest release, but you can see it's a pretty big, long laundry list of functionals. Some of them are developed for very specific things. Gaussian has a habit of just, implementing as much as it can so that you have it at your disposal. You will find that different programs implement different amounts of the functionals, okay? And some have specialty functionals that you can't find in other pieces of software, okay? So not all of the functionals that have been developed are available in Gaussian, and Gaussian has some functionals that aren't available in other programs. Okay. So how do you choose your functional? It is a very good question. And historically, I used to say, all right, if you don't know, of course, you go to the literature. If you can find something in the literature where they benchmarked on a very, very similar system, you run with that one. If you can't find anything in the literature and you don't have a lot of phenyl-phenyl interactions, I will still often say, you can start with B3-LYP or BP86 because it's a nice stable functional to get a feel for how your system behaves. And then you can move on to one of the more specialized functionals that might get you more accurate results, but take longer to finish. Okay. So that's always a good plan of attack. But number one is don't just blindly use a functional. Okay. It's just like you don't blindly choose your reagents for a reaction. You go look at the literature. and see what's already been investigated and what works well. Okay, so there's also something called double hybrid DFT. With double hybrid DFT, you're including not only Hartree-Fock exchange, okay, and DFT, but MP2 in the mix. And this is to correct for the missing dispersion that is in most implementations of DFT. But it's about at the cost of MP2. So the first question that I usually get at this point is like, okay, well, why don't I just do an MP2 calculation? Well, if you remember this morning when we did molecular oxygen, the MP2 results weren't that great, right? They still had, the bond distance was still not very good. Okay. So MP2 by itself overestimates the dispersion, whereas Hartree-Fock or DFT underestimates it. So the hybrid DFT is getting that balance for the dispersion interaction between the DFT and the MP2, but it's at the cost of MP2, so it's computationally more intensive. So the holy grail would be if we could get MR multi-reference DFT working. And I see it, blips of it here and there, but so far really not much in the way of implementation, because that would give you multi-reference calculation that includes dynamic electron correlation at about, the cost of doing a CAS-SEF calculation. It's still expensive, but at least you would have the electron, the dynamic correlation along with the static correlation. Okay. So hopefully at some point in the future, this will work. Okay, so DFT is pervasive in the literature. Usually when people start doing calculations on something, that's the first thing they do is a density functional theory calculation. And the reason is because it includes that all-important dynamic electron correlation for high-quality results at about the same cost as Hartree-Fock theory. Okay. Often it's more robust for systems with multi-reference character, especially with transition metals, but just like everything else, it can have catastrophic failures. The biggest drawback of density functional theory is the no hierarchy. So in the ab initio series, you can go, Hartree-Fock, MP2, and up the ab initio series, and you know that you're including more and more dynamic electron correlation in a hierarchical fashion. That's not true with DFT, okay? Going from, LDA to GGA to hybrid GGA to tau GGA, that's not a hierarchy. That's including different electron correlation, different exchange energy, but it's not hierarchical. Okay, so there's really no good hierarchy. Going from one functional to another is not necessarily going to get you more electron correlation. It's just going to get you different electron correlation. Okay. Historically, it's been poor for dispersion, but they have added on a lot of either empirical corrections or functionals that are better developed for dispersion. To get that. So it's not as bad of a con as it used to be. And pure DFT tends to overbind, but it's not too bad. I really should probably remove that one now. Oh, pure DFT is where you don't have Hartree-Fock exchange. Okay, that's what the pure DFT is. Okay, so that pretty much covers density functional theory and the basics of it. Okay, so I also want to talk a little bit about molecular mechanics, because we're going to use that during our hands-on session with a method called ONIOM, where we have a hybrid approach. Part of the molecule is at a high level of theory and part of the molecule is at a low level. And our low level is going to be molecular mechanics. Okay, so I just want to touch on this topic because as you go to very large systems, you will often be doing something at multiple levels of theory. So molecular mechanics is very different. We no longer have electrons. It's all classical in nature. Your energy expression is just the force field. And the force field looks something like this, where you have a bond term, an angle term, torsion term, and some other things, okay, maybe an out-of-plane term. So, Hooke's law, you have two balls on spring, and that's your description. Where the spring constants come from, that usually comes from quantum calculations. And historically, it's been from Hartree-Fock calculations. Okay? But it could also be from DFT calculations or something higher, like couple cluster calculations. So that's where the spring constants come from. So that has to be parameterized. So molecular mechanics is heavily parameterized. And then the implementation, there's no electrons. Okay? So that means you cannot change the bonding. Okay. Okay, so that's what I'm specifying here is that generally it's not suitable for reaction mechanisms because you cannot change the connectivity because the energy expression completely changes. There is one specialized that I know of on force field, the reacts force field. There might be another one, but I think it's still just the reacts force field that lets you make and break bonds, but it's very special and can only apply to a very specialized sets of molecules. You have to do a lot of parameterization to apply it to something new. Okay, so it's heavily used more for relative energies, okay, and different conformations of those molecules, but no bond breaking information. Okay, so this is what, you know, class 1 force field potential might look like, where you have the spring constant, you have an equilibrium bond distance. When you stretch it, you know, it goes up quadratically. There's your quadratic bond term. Same thing for angle and torsion, impropers. Okay, so that means you have to have spring constants and equilibrium distances, angles, and torsions for every type of bond and angle and torsion that you have in the system. Okay, so it's a lot of parameters. Then you're also going to have intermolecular interactions, which goes to the electrostatics and the van der Waals. So this is the electrostatic term, and this is the van der Waals term. Okay, so what we're going to focus on is this rules-based force field. The rules-based force field lets you apply it to most of the periodic table. Most force fields stick with, you know, first, second row main group, carbon, nitrogen, oxygen, sulfur, phosphorus, standard connectivity, heavily used for proteins, DNA, things like that, organic compounds. The rules-based force fields have parameterization for, like I said, most of the periodic table. The quality of the results is the more quantum effects you have, the lower the quality of the results get when you're using these rules-based force fields. You have to tune your force field to specialized systems. Okay. Okay, so like I said, we're going to focus on this universal force field, but there's a whole laundry list of force fields that are available that are heavily used for different things. In the interest of time, I'm going to pass on here. Okay, so for the universal force field, and this is true of all molecular mechanics force fields, is it determines the spring constant and the other parameters based on the atom types. And the atom types are determined based on the connectivity in your system. Okay, so I have an element that's singly bonded to some other element. So it assigns a very specific atom type to that element that is singly bonded to the other element. The atom type has a very specific name that was designed for something special. So with the UFF force field, you can tell what the parameterization is for based on the name. So the first two characters are going to be the element, right? The third character, if it's present, represents the hybridization state. So if it's 1, it's going to be linear SP, right? 2, SP2. Trigonal. R means it's involved in resonance, like in benzene. Okay, 3 would be tetrahedral, and since UFF applies to the periodic table, if we go to the transition metals or some of the other ones, they can go to the hybridization, higher hybridization states. 4 for square planar, 5 for trigonal bipyramidal, and 6 for octahedral. Okay. For some specialized ones, there might be 4th and 5th, which would go to boron or oxygen and like zeolites. And you might have something instead of the hybridization, after the hybridization state, the oxidation state. The oxidation state, in my experience, has often not matched the atom type that gets assigned to it, which sometimes is fine. It really depends on what results you're getting. The oxidation state is not as critical in a classical simulation. It's more of the hybridization The hybridization has to be correct. If the hybridization is wrong, your results are going to be really bad. Okay, just one other little detail about the universal force field is you do have this thing called a bond tuning parameter, and the bond tuning parameter lets you tighten up or loosen the springs, which becomes important for transition metals. When you have transition metals attached to some other element, if it's, you know, your first calculation, it's too loose, you can increase this bond tuning parameter to tighten up the spring constant. So here's just an example of a system that was done with UFF, and here are the atom types that are assigned. So we have the platinum, we have it as square planar, we have N_2 because it's an sp2 nitrogen. This nitrogen is involved in resonance, so it's an N_R. Okay, so when you're doing these simulations that include a classical component, you want to check your atom types to make sure that they've been assigned properly. Okay, so what are we going to use the molecular mechanics for? We're going to use it in ONIOM calculation. When you have a very big system, sometimes trying to do the big system at the high level of theory, even density functional theory or Hartree-Fock, is really computationally intensive or out of reach. So it can be beneficial to use ONIOM or QMMM methods where part of the molecule is treated at the higher layer, which is usually like DFT or some other quantum level, and then the entire system is treated at the low layer. Now with the ONIOM, since the entire system is treated at the low layer, that means you have to have parameters for every single atom in the system. There are other implementations that do like QMMM, and it cuts it, and the low layer is not applied to the entire system. It's only applied to part of it, okay? But you're far more restricted on what you can apply it to. Okay, so the ONIOM method allows you to apply it to a wider range of systems as long as you have a low layer level of theory that can be applied to the whole thing. Okay, so the one major point that I want to emphasize for the ONIOM method is when you choose your region that you're going to have for the high layer, which is, like I said, usually some quantum level, you have to cut across a single bond. You cannot cut across a double bond, because what it's going to do is it's going to cap this region with a link atom, and that link atom is going to be a hydrogen, and that's what's shown here. Okay, so you cannot cut across a double bond. You won't get the right electronics, and your results will be really bad. So that's one of the major things when you're setting up this type of ONIOM calculation is you have to make sure that you cut across a single bond or no bonds, right? So if you have a molecule inside a binding pocket, then just the molecules in the quantum range. So with an ONIOM calculation, things that are going on in the quantum area can do bond breaking and formation, but not in the molecular mechanics only region, okay? So this is just showing that, you know, there was a ramp up of ONIOM, and then it started to lag off a little bit. I don't know what it is past 2014. You don't see this in the literature all that much because they are somewhat difficult to set up and perform, but it can be very useful for large systems to implement these ONIOM type calculations, but they do take a lot of work. So this is just an example of using ONIOM calculations to decrease the computational cost. They were able to run this on a much smaller system. They didn't have big systems available to them, so they put the big bulky part that was not involved directly in the reaction chemistry in the molecular mechanics realm, and then investigated the reaction at the quantum. Okay, so it allowed them to work on a much smaller computer. This is an example of when you're working with proteins. So if you're ever interested in working with proteins, often people will prune down the protein and they'll take it off. And then they will try to run the DFT or some other level of theory calculations, usually DFT, and look at reaction chemistry. The problem with that is there can be a substantial change in the ligands. And if you just start freezing them, you don't get the flexibility that it might need while it's doing the reaction. But you need to have them somewhat restricted because they're attached to a protein backbone. So when you do see things like ONIOM or QM-MM being performed, often it's in the realm of proteins and reactions at active sites. That's one common use for it. So for this one, this is the oxygen evolution complex in photosystem 2. If you try to look at the property of interest, the transitions, without having the protein around it and having the waters, you don't get proper results. You don't get good results. Okay, so ONIOM calculations allow you to incorporate both the molecule of interest at the high level of theory plus the surrounding classical environment that has a strong impact on the electronics of the quantum part at a reasonable computational cost. So I just want to mention this one briefly because I said, you know, with the ONIOM, you have to have the low level of theory across the entire system, but there's other implementations where you can do a quantum area and a molecular mechanic area, and the lower level is not across the entire system. Schrodinger has something called QSite that's implemented. This is not free software. It's pretty expensive, but you can get it. If you're at A&M, you can get it through the LMS. If you're not at A&M, you can inquire in your home department to see if they have, if anybody has the QSite software. But it's very special since you don't have it applied across the entire thing. It's limited as to what they have implemented as fitting functions across the bond that you're cutting. Okay, so it's limited on what it can be applied to, whereas ONIOM is pretty much, you can apply it to anything that you can find parameters for the low layer. Okay, so if your low layer is Hartree-Fock, you can apply it to pretty much anything. Okay, so that's the major difference between the ONIOM method and the QSite. It's the flexibility. Okay, okay, let's go ahead and take a, we'll take a 6-minute break, and then we'll work on the next hands-on session. So we will resume at about 2:55. Okay, let's go ahead and get started on the hands-on session for this afternoon. So like I said, we're going to be doing an ONIOM calculation where our high layer is density functional theory and our low layer is molecular mechanics using the universal force field, which is that rules-based force field that I talked about during the lecture. So if you haven't done so already, please log into the video portal. Okay, and you should find on your desktop 2 PDB files now. Okay, these are protein data bank files. Okay, and those are the files that you're going to use for your starting structure for these calculations. Okay. I also want to comment that I updated HS3 with the full path in there. So that is a new file that I pushed out over the break with that updated information. Okay, so let's go through what you're going to be doing for the hands-on session 4. So this is going to be our molecule of interest. It's a molybdenum dioxo species, which is an analog of molybdenum oxotransferase. This is a very large system, reasonably large system for a DFT calculation. It is doable these days. Back when I did this a long time ago, it was really not doable on the computer systems at the time. Today, you can definitely do this on the computer systems that we have today. However, if you do the entire system with density functional theory, you run into some problems, and this goes to the dispersion interaction. Okay. So we have a lot of phenols. We have tert-but phenols. In the crystal structure geometry, everything is sort of spread out. You're going to be doing a calculation on 2 different conformations. This is the crystal structure geometry, and this is another conformation that's available to this system. And you'll notice that there's a lot of congestion over here, right? There's a lot of interaction of the hydrogens, the methyls are very close to each other. There's some pi-pi stacking that goes on. So this is a very strong area where you would have dispersion interactions. So if you use traditional functionals without a correction, you might not get very good energetics to compare the difference in energy between these two. Okay, so looking at this molecule, this would be an indication that if you were going to do the entire system with density functional theory, that you should use one of the dispersion corrected functionals. Okay, if you want to improve the energetics between these two conformations. Okay, so instead of doing full DFT calculations on this, because if we did that during this class, you wouldn't get your results until either tomorrow or late tomorrow, most likely, especially not on this system, maybe on the bigger system or the one with newer CPUs. Okay. All right, so we're going to set up calculations on this structure and the other conformation. We're only working with structure number 1. Okay. So one of the questions I get is, I mean, why would we do calculations on anything but the crystal structure geometry? So the reason is that the crystal structure geometry is not necessarily the conformation that you have in solution. In the crystal structure, there's other effects. There's crystal packing effects. You have a lot of intermolecular interactions, which can have pi stacking and other favorable interactions that can lead to a higher energy conformation of the molecule to get overall stability of the crystal. So the crystal structure conformation is not necessarily the one that you see in solution. And if you're looking at reaction chemistry in solution, the reaction may be occurring with a different conformation, which may have consequences. And in this case, it's reacting with the oxygens. The crystal structure conformation has phenyl rings sitting right on top of the oxygens, which blocks them from reacting as much, the lone pairs that are available on the oxygen. The other conformation has the oxygens exposed. Okay, so it would be useful to see what the difference in energy is between these two conformations to explain some of the reactivity in solution. So to do that, we're going to do ONIOM. Okay, so we're going to treat these things here that have that are solid in the quantum realm, okay? And then we're going to treat other parts in the molecular mechanics. Okay, so this is a breakdown of what we're going to put in DFT. Okay. So I would like to ask you why I have drawn this the way I have. Okay, so I'm including this entire ring in here in my DFT component. And we have, this is a pyridine ring, so we have a double bond here, a double bond here, and a double bond here. So it increases my computational cost to include this whole ring. Does anybody know what would happen if I tried to draw the cutoff here and just include the molybdenum and everything directly attached to it, which has most of the electronic effect? And if I tried to cut along here and do the ONIOM calculation, right? You can't go through the double bond because it's going to add a link atom, and that is not the correct electronics. So I also don't want to cut right here because sulfur attached to hydrogen is not a very good representation of sulfur attached to carbon, okay? And it's directly attached to the molybdenum where I'm going to have most of the electronic quantum effects, okay? So a good sort of middle ground is cutting around here and inclusion of this. And then everything else is in the molecular mechanics. So I've still decreased my computational cost substantially because remember DFT, it scales at about n to the 2, so it's quadratic. So having all of these tert butyl phenyl rings in the molecular mechanics and not in the DFT will substantially lower the computational cost. Okay. And if you don't include these ligands, you don't get the right electronics. You only have one conformation available to it. These big bulky groups are what cause multiple conformations to be available for this system. All right, so the way that we're going to be setting this up is with Gauss View. So you're going to use Gauss View to open the PDB files that I gave you. Okay? And when you open them with the Gauss View, I walk you through how to set things up. Now here's the trickiest part about molecular mechanics is getting the atom types assigned properly. This is the point where connectivity becomes everything. So somebody couldn't find the PDBs on their desktop. Is anybody else having that problem? So if you don't see the PDBs on your desktop, what I would like you to do is go ahead and open your home folder and your desktop and click refresh and see if they magically show up. So the desktop often doesn't refresh itself automatically. Yes, good. That's the problem with graphics. I'm a command line kind of person. The command line, it's always going to show up. In the graphics, you have to refresh it. Okay. Okay. So if anybody else still is missing the files, we'll get to those after I get done explaining. Okay. Okay, so we're going to load these with Gauss View, and we're going to use Gauss View, the graphical interface, which is a separate program, to prepare our ONIOM calculation instead of trying to make a manual input file. And once you see the input file, you'll understand why we're using the graphical interface to do it for us. Okay, because it gets far more complicated when you're doing molecular mechanics. You have to assign all sorts of things to it, including the atom type. And with the ONIOM calculations, you also have to add the link atoms onto it. Okay, so we're going to load the PDB files with Gauss View. Please carefully read the instructions and try to follow them verbatim, because if you skip a step, you're going to run into problems. Right. So one of the things that becomes very important once you load the PDB files to make sure that the bond orders are correct. So let me go ahead and get to my command line. And I'm going to make sure that I've loaded my module. Okay. And then I'm going to load this first one up. So you should see something like this. I'm going to go ahead and zoom in, and you'll notice that Gauss View has done all sorts of interesting things with the bonding. Gauss View will do all sorts of crazy stuff with the bonding. It's common. So you don't really worry about what it draws for bonds. You're more interested in what the distances are when you're doing a quantum calculation. But the minute you put molecular mechanics in the mix, you have to be very concerned as to what bonds are drawn, because the atom type that it assigns depends on the bonding. Because remember, with molecular mechanics, it's all about, this is my element and I have it bonded to these atoms with this particular bond order. Okay, so the first thing that you need to do is fix the bonding. So if you right click, okay, there's a builder option and there's a modify bond, which is shown up somewhere that I can't see. Where'd it go? The magical missing modify bond. Okay, let me just try something real quick and see if it will. There we go. Okay, I don't know where, okay, right. So once you go to the bond editing, you have to click on the two atoms that you want to modify, and we need to add this in as a single bond. Okay, and you'll need to do this for all of them. Okay. But for the molybdenum oxygen, that should be a double bond. If you do not fix the bond orders, when you go to apply the molecular mechanics in the ONIOM, it will give you the wrong atom types, because it will then apply an sp3 oxygen atom type. and that's not correct for this. Okay, and if you don't have this bond here at all, there will be no spring constant for the molecular mechanics level. Okay, so you need to make sure that you come through here and modify those bonds. Once you have the bonds modified, then you can go through and follow the other steps. Okay, so that's how you go about modifying the bonds. Just do builder, modify bond, and I'm sorry, nothing pops up at this point. It's not until you click on the atoms that it does. Okay, and then you can modify the bonds. So single bond, single bond, single bond, single bond, double, double. The rest of it should be correct. Okay. Okay, so the next thing that you're going to do is to open the tool select layer. Okay, the layer is where we're going to assign some things in the low layer and some things in the high layer. And the first thing that you want to do is put the whole thing in the low layer. And if you put the whole thing in the low layer, so we're going to go to the tools, right? Yeah, select layer. Make sure this says low, you select all, and you apply. And you'll notice it becomes lines. Now, if I come here and I click on the molybdenum, I can expand my selection. But I can't go any further because if I expand my selection for the high layer, it's going to go into these phenols that I don't want to expand to. So I'm going to go ahead and say, apply that to the high layer. Okay. And then I can come out here and say, select this hydrogen and expand, right? And apply that. And then go here and expand and apply that. And then you just want to rotate, make sure you haven't missed anything. Does anybody see where I've missed something? Yes or no? Have I missed anything? It's hard to see, so you definitely want to scrutinize it because I have definitely missed something. I am missing hydrogens right here and right here. And that's going to cause a fair bit of problems if I try to do that, okay? So now I have everything in the high layer that should be in the high layer, okay? And the rest of it in the low layer. So my bonding is correct and everything else is correct. So I can go ahead and close that. And then when you go to do the calculation, Gaussian calculation setup, there's a couple of things that I want to point out. Okay, so for the job type, we're just going to be doing an optimization, no frequency. Okay. When you go into the method, okay, I tell you what method to use here and what basis set. This only has a small number of the functionals that are available in Gaussian. You can see this is a very small number, and it doesn't have the one that we want to use today. Okay, so I just have you use B3LYP, and then we're going to change it in the input file. But when you're doing the ONIOM calculation, you need to make sure to turn this on. And then you're going to get a high layer and a low layer. You need to make sure that you have everything set up here as far as the layers and the bonding before you apply this. So we're also using Lanol 2DZ here. So here we go. And then for the low layer, you're going to choose mechanics and UFF. This is the step that's going to apply the atom types for you. Never hit submit, click retain. And that will have applied the atom types. The other thing that you're going to need to be able to do is see the labels. Okay. So what you're going to want is that molybdenum is atom 2, oxygen is 1, okay, and then it's 3, 4, 5, 6. So I'm going to save this real quick. I haven't quite finished everything, but I want to show this to you. So make sure when you're saving it that you change the type. All right, you want a Gaussian input file and make it .com. Okay, so I'm going to go ahead and save that. And now that's on my desktop. See, sometimes it updates and sometimes it doesn't. Oops. Open the terminal again. Okay, so I'm going to take a look at the file that I just created. And I want to show you a couple of things. Okay, one, I have all this extra stuff in here, and that's because I skipped a step. So I'm going to go back and show you that. But the other thing that I want you to point out here is that we have, here's my ONIOM, level of theory, basis set, colon, another level of theory. So this is for my high layer, and this is for my low layer. And then I have this geom equals connectivity, and this goes to the connectivity at the bottom. And then I have three listings for the charge and multiplicity, and that's because we have the high layer, we have the low layer, and we have the thing in between. Okay, so it lists it 3 times. This is the connectivity section down here. For a standard DFT quantum calculation, this section does nothing. But for molecular mechanics, it does something. Okay, so this is for that bond tuning parameter, and it tells the molecular mechanics component what's a single bond and what's a double bond. Okay, so it has to know how it's bonded. So here we have atom 1 is attached to atom 2 with a double bond. Okay. So if we come back to here, atom 1 is attached to atom 2 with a double bond. So this is one of the things that I want you to double check. It should be the first 2 lines that have all the bonding that you need to check for the connectivity section, but you should check to make sure that these are double bonds and these are single bonds. Because if they're not, if they're all single bonds, you're going to get poor results, okay? Or it's not going to work at all. It'll never finish, okay? All right, so you definitely don't want this PDB name stuff in here either. And the way that you keep from having the PDB name in there, it tends to throw Gaussian for a loop, tends to do bad things. So to get rid of that in the general section, you turn this off. So it's part of the instructions is to turn that off, the right PDB data, and then it won't be in there. Okay. And I think those were the major things that I wanted to point out for setting up the ONIOM calculation. Okay, so the one other thing is once you get done setting up your first one, save the COM file, submit it right away. Okay, because these calculations are going to take substantially longer than what you did this morning. What you did this morning and yesterday finished like that. Spoiler alert, this calculation is probably going to take 20 to 30 minutes, which is still fast in the quantum calculation world. Okay, but it's going to take substantially longer. So once you set up the first one, save it, submit it, leave Gauss view open. Because if you did make a mistake setting it up, you don't want to have to start from scratch. So leave this window open, don't close it. Okay, just open, file open the next one, okay, and start processing that one. And then submit that one. And then the last thing that I have you do while those are running is set up a pure UFF calculation, completely molecular mechanics. Those calculations take about 1 second. They're very, very, very fast. If you set them up correctly, then you should get a reasonable result back very, very quickly. So once you've submitted your ONIOM calculations, go ahead and set up the pure UFF calculation. When you set up your pure UFF calculation, because Gauss view is already open, so it's going to remember some of your settings from before, make sure that you turn this off. It should only say one thing here. There shouldn't be multiple layers available. Pure UFF isn't an ONIOM calculation. It's just mechanics, okay? Okay, so make sure that that's turned off. All right, so I think that's all I wanted to show you about setting these up and running them. So what I will do is at 3:50, I will come back on and go over some of the results with you. Okay? Okay, so go ahead and get started. And of course, if you run into any problems, please prompt me in chat. And if you want me to take a look at what you've put into your high layer to make sure that you have everything in there that should be in there, please put the view only link in there and I'll take a look and let you know if it's done correctly. Okay? Okay, so I'm going to go ahead and stop recording now. Okay, so hopefully everyone was able to at least get the 1-low.com and the 1-chris.com set up with the appropriate high layer and low layer and submitted to the queue. Okay. One of the really nice things is that once it's submitted to the queue, it will keep running after you log out. Okay, even if you close your Open On Demand portal or log out of the Open On Demand portal, your job in the queuing system will continue to run until it either hits the wall time that you asked for, or Gaussian crashes out, or it finishes normally. Okay, so if you've submitted those, they'll keep running, and we can take a look at them tomorrow during the morning hands-on or the afternoon hands-on, time permitting. Okay, so let me go ahead and close this, and I just wanted to show you a couple of things. Okay. Oops. This here. Okay, so I ran this a little bit earlier today, and it ran on 2 cores. And when it was running on 2 cores, it took, the job CPU time was 1 hour and 43 minutes, and the elapsed time was 52 hours. Okay, so we're running this with more than 1 processor. I was conservative in what I ran it with only 2. But the difference between the job CPU time and the elapsed time is the real time, what's on the wall, how long it took from when it started to when it ended. The CPU time is somewhat misleading. Okay, the CPU time makes it look like, you know, you got what would be considered perfect, almost perfect speed up, or better than perfect speed up, because the wall time was half of the job CPU time. Okay. So if you really want to know if your program is running efficiently across multiple processors, multiple cores, you really have to run some actual benchmarks and compare wall time. So if you run it with 2 core, you'll get a certain wall time. And then if you run it again with 4 core, you'll get a certain wall time. And what you would like to see is the 4 core takes half of the amount of time as the 2 core. Okay, most programs will show you something like this where it says, you know, elapsed time, job CPU time, or something along those lines, but you can't really gauge based on this job CPU time. Okay, so my calculation on 2 core took 52 minutes, okay, which is substantially longer than what we did earlier today. So that's why I say if you got them set up and submitted them, you can just let them keep running, and they should be done when we come back tomorrow. Okay. Okay, so it is a little bit different when you're doing an ONIOM calculation. You have more convergence that needs to occur with the ONIOM calculation because you have the DFT level, you have the high level and the lower level, and it has to map between them. So you have maximum force and the displacement at the DFT level, and then you have a maximum and RMS for the force at the molecular mechanics, and both levels have to be converged. So you end up getting multiple yeses. So geometry optimizations take substantially longer in the ONIOM method because of the fact that you have to converge both the DFT, the high layer, the low layer, and the mapping of the 2 together. Okay. So let me just, I'm going to pull this up with Molden, hopefully, after I load my module. Oh, and for those that don't know, in Linux, if you hit the up arrow, it'll scroll through previous commands. Okay, so here's my structure. Okay. If I click on Geom Convert, it shows me how many steps it took. So to converge this, it took 17 points. Okay, 17 geometry optimization steps. Not a substantial change in geometry. Okay, this was already a fairly optimized structure, but it still took 17 steps to optimize. So you can imagine how long it would take if you had had a bad starting structure. Okay, so 17 steps, very little change. When it comes to the ONIOM calculations, if you want to get the energy out of it, you can grep for extrapolated. Okay, and it will give you the ONIOM energy. Some of the other grep commands like HF equals, done, are also in there. But when it comes to ONIOM calculations, the ONIOM energy is the line that has the extrapolated energy on it. Okay, so if I want to look at that one, which is taking a lot more geometry steps, I'm going to go ahead and print just the last line. Can anybody tell me why I have so many extrapolated energies in my log file? Why don't I only have one? Does anyone know? Have an idea? Let me go back to Molden. Right, it's calculated every geometry optimization step, every iteration, okay? So I should have at least 17 of them. And it's the last one that is the final one, as long as I have normal termination, okay? So you always want to check to make sure it fully converged, which is what I looked for with the threshold. And when you grep for these things that are printed at every single geometry step, you can add on this pipe tail, so it'll just print the last one. So I'm going to do the same thing with this, okay? And here's the other part that tends to throw people when they start doing quantum calculations. The more negative, the better. That means the more stable it is. Okay, these are not orbital energies. This is the total energy of the system. So here is the energy of my low structure that I name low. And here's the energy of the crystal structure conformation. Okay, and you can see that this one is lower because it is more negative. So let's go ahead and calculate that out. And these are in Hartrees. By the way, BC is the binary calculator. It always seems to be available. Oops, I scrolled. I'm on Linux, so it's handy. Okay, so I'm getting a 6 kcal difference in energy with the low or open conformation being 6 kcals lower than the crystal structure conformation. Okay. So this is a really important concept because a lot of people really, they look at a crystal structure and they think that's the conformation. That's the conformation of that molecule, no matter what environment it's in, that everything should be that conformation because that's what crystallized. But the crystal packing effects can have a substantial effect on the conformation of that molecule. Okay, so what you have in the crystal form is not necessarily what you have in solution. Or not necessarily what you have in gas phase if it's also something that you can get in the gas phase. Okay, but usually it's something in solution. We will talk about solvation in the lectures tomorrow, and we'll do some calculations including solvation. Okay, right now the only thing we've done are gas phase calculations, no solvent whatsoever. Okay, there's no solvent interaction, nothing available. Okay, so tomorrow we'll talk about solvation, which is an important contribution and needs to be included carefully when you're doing these types of calculations. Okay, so I'm not going to show you the actual energies that come out of the UFF, but what you should get as a difference in energy for both the ONIOM calculation between the low and the crystal structure and from the straight UFF should be close to 6 kcals per mole, where the open conformation is lower in energy than the crystal, which explains the experimental result. That the barrier is the same if you calculate it in the open conformation as opposed to the closed conformation where the phenols are sitting on top of it.
Okay, so it's the low energy conformation that is the important conformation for the reaction. So I did have a question about when the videos go up. It takes time to process them. I do not have an answer for that as of yet. Okay, hopefully I will have a definitive time frame for when and where they will be posted for you tomorrow. Okay. Okay, so that's it for today. I will stay on the line for a little bit if you have any additional questions. Otherwise, I will see everybody tomorrow morning bright and early at 10 a.m.